Mars structure in Central Europe sparked a wave of scientific interest known as the Mars fever. That's a very, very great research. Currently, he also serves as a co-editor of the Bulletin of the Geological Society of Greece, and he is an active member of several professional organizations, including what is the CSEG, EAGE, SPE, IFJ, and IAEG. I don't know what the organization about, but I think maybe later Mr. Malina will tell us about that. Okay, without any further ado, I'm pleased Mr. Dr. Jan Malina, who will be delivering his presentation of the application of gravity surface in geoscientific research and exploration. So please, the time is yours, Mr. Jan.
First of all, I wish to greet everybody who is coming to this meeting. And mainly, I thank you, the chairman, and also the big chairman of the Congress, Mr. Richard Leverisa. Thanks very much. Terima kasih. And I will go to the presentation. Can you see that?
Yes, Mr.
Yes.
Okay, so I am a geophysicist, and what I want to say or speak about is how we can apply this technique, I mean gravity, in different aspects of geoscience for solving problems which we may face. This is an older gravimeter Lacoste and Romberg, and the environment, as you may see from the background, is a volcano. So this will be one of the topics, but later, maybe at the end of the talk. So what I want to show, what is gravity? Because not everybody is very familiar probably with gravity. What is gravity survey? How we can do it? What is important? And what is it good for? So why we do it? Yes, mineral exploration, hazard for people, and even finding some treasures. So the question for students, if there are any, who was one of the first principal gravity guys? This man? It's Galileo. You see when he was living, and because he contributed a lot to the beginning of gravity, we called gravity unit milligal after Galileo, and we use it commonly in exploration and science. So he did, for example, the test if you have two bodies or three bodies, doesn't matter, and they have different weight, if they really fall to the ground with the same speed. Normally you think no, but in reality, yes. Why? This is the experiment he did in Pisa in Italy. And you see, the idea was that the small weight will fall slowly, but no, both of them, they fall same speed because of gravity acceleration. So what was probably the first gravimeter? Yes, this is the first gravimeter. Why? Because this guy, he was watching why the apple falling down, and he think there must be some power to move it down, and he developed Newton's law of gravity, which you remember from elementary school probably. And well, we have gravity, everything is falling down, but the bird, no. The bird is beautiful, flying in the air. So why he is not falling? Because he is capable of flying. But I was trying to do the same thing and to check if there is really gravity acceleration. So I did this test from 3,500 meters falling down. It was really accelerating, so I can confirm myself there is gravity acceleration. It was actually a wonderful experience. So what are the problems if we do gravity survey? This is Saudi Arabia, and you see the big dunes, which have even 200 meters elevation. So you have to go with the car, do gravity survey, cross the dunes, and if you are lucky to cross the edge here, this one, then you can nicely go down 100 meters. It's fantastic, but risky. The terrain is important for gravity. Why? Because it impacts what we read with the gravimeter. So for that reason, we have to do so-called terrain correction. This guy is trying to use some small clinometer to estimate what are the shapes of the field. Why we do it? You see the black contours, they are like crazy and really not very nice to describe gravity field because of terrain corrections. After you apply terrain correction, you get the blue isolines, which are pretty good. Another problem is you have a gravity base in the desert, but you come next day and it's lost because it's under the sand. So you spend 1 hour to dig it out. Or another case, contrary, the sand is gone and the base is up above the ground level. So there are some issues to handle. And maybe for you, this is more familiar. Why? Because this is Papua. So to do survey here is crazy difficult, I can tell you, and you can imagine yourself, you know your country. So you have to cut the trees, you have to do the ladders, and it's very, very difficult for moving. Also, we have to deal with a very tough topography. And the reading of gravimeter may be really complex because it's difficult to move, it's muddy and slippery. So you have to be careful, you have to be always on the stairs. So it's really difficult. Sometimes raining, sometimes difficult from different reasons. This is in my country on the open pit coal mine when they cut the trees first, etc. It's difficult inside the mine because of the machinery which is working and making a lot of noise for the gravimeter. But the geology is also interesting. So let's go to the examples. This is the first one. You see the date, the year. It's like 130 years ago, and in Hungary they developed so-called torsion balance, which was like measuring gradients of gravity, and it was applied for actually oil exploration because maybe you see the tower at the back. It's a primitive oil exploration drilling. Okay, current status of what we can do in oil exploration or something like that. This is a case from Germany. You see, this is the Bugge anomaly, which is the result of basic processing of the gravity data. You see some blue color, which is usually negative in gravity. It's a salt diapir. Salt is one of the big targets for gravity because it has very low density, so it's relatively easy to recognize. But the client here, he was interested to see detailed morphology of the top of the salt body because it was hidden underground. So he very much liked the separation for horizontal gradients or some residuals. And For example, this place here was of high interest because they were interested to do a gas storage somewhere on the top of the salt body. So it was about 3,000 points to measure. This is from example from Oman. How gravity can recognize something. We have a flat topography and a sharp mountain in this place. And the geologists, they were thinking there may be some structure at the big depths, which could be the trap for oil. So it was not clear what is here. So they did some modeling. And if they have a structure here, they actually see discrepancy between what they measure and what is in the model. So they removed the shape down here, they cancel, and they got some fit. But be careful, this is the topography from satellite. This is the topography from ground. And the question and problem was that the old gravity data were not measured on the mountain. The guys were lazy or they did not wish to climb. And during the new survey, I decided we must go on the top of the mountain to be sure what data we have. So I push on the crew and we climb to the top with the gravity meter. And what do we get? Significant change of the gravity map, because this red anomaly, which is positive, was not existing in the old data, and it completely changed the interpretation of the story. Here we do some structural and tectonic analysis. We need rock densities to know from samples. And here we have the model. So I did the same what they did, no structure at the depth, but I don't have a good fit of the data. So then I add back the structure at the bottom of the geological section, and I got good fit. So it's not 100% sure, but it shows that gravity may really improve the geological knowledge from the depths and to contribute to the decision making about the exploration. Another example was here. This is also gravity map from, I should not show it, it's exclusive data, but from the Middle East also. And the guys, they did drilling somewhere here, but they did drilling exactly on some fracture zone, which was not very positive. So normally, if they have this new gravity map, they should put the drill somewhere here on the slope of the anticline. So this was for exploration, let's say for hydrocarbons and salt bodies, etc. But we are dealing also with much smaller problems. So we need microgravity. It means that we have to be very accurate. And in exploration, 10 milligal is an anomaly which we are interested in. In microgravity, we have to be 1,000 times better in the resolution. So 10 microgal already is an anomaly. This is an example how they measure in the field, but is good for exploration, but is not good for microgravity. Why? Because the GPS antenna is stuck in the sand. We don't know exactly how deep. The gravity meter is not measured the height above the ground, etc. And all this contributes to the error in the data. So in microgravity, we have to be very careful. Now, I show you some gravity meters. Who does not know? This is Lacoste, Buris, Sintrex, digital Lacoste, and this is a girl, for example, also working with gravity. And this is CG5, which is usual gravity meter. But we have the best in the market, which is Sintrex CG6, is an excellent instrument. And hopefully, if we make some good decision, we can go to Indonesia and cooperate with this gravity meter. Mr. Richard is listening, I hope. Okay. So you have to be very careful. You have to play with your gravimeter, do whatever you can to understand how to measure perfect data. And then you can start looking for small objects like voids of whatever origin, caves, voids, cellars, tombs, whatever. So if you have a big void, you get big negative anomaly because there is no mass in the void. So the gravity attraction is smaller. If you have small one, you get small anomaly. If you have flat one, it's difficult to recognize because it's flat and not sharp. So how these voids may originate. For example, this is from coal mining. You mine the coal and the roof of overburden gets disintegrated, falling down, you can get sinkhole, which is a collapse of the surface. Another case, if you have limestone bringing water, also we can produce voids underground. And if you measure gravity on top of here, you can recognize that there is something like that. And it may look like this. And you can imagine this is a catastrophe. So it's an environmental issue and safety issue, hazard issue. So this is from Central America, where they have also karst at the depth of about 30 meters. And the karst has very aggressive water, which can remove the sediments, as I showed before, and then you may have a collapse here. So this is very obviously very critical issue. The process was something like this. Another cave in this one is in Qatar. So you see how big caves actually can originate in different places in the world. I tried to calculate what would be the gravity effect of such a void, of such a big cave. And you see, this is the red lines are showing the accuracy of the survey. And you have big negative anomaly, which would locate such cave very nicely. And you have some caves in other countries too. And you may understand which country is this one. Similar problem may be also in Indonesia in some places. For example, what can the karst do in gravity? This is a karst block, let's say. So there is a decrease of density, and how you can help other guys. If you know that there exists something like this, you can recalculate into seismic velocity, and you get also negative seismic velocity difference here, which is important for calculating static corrections for seismic survey. So detailed gravity can help seismic survey in this aspect. We did microgravity in one country in the Middle East. There was a small town, already people living in, and suddenly there was a big hole, big collapse of the surface. So they removed all the people, maybe 2,000 people they removed. And we did microgravity and found these red anomalies, which indicate the holes. Then they decide, okay, we have to fill the holes with the material. So they spent 1 year doing this terrible job. And they ask us, please come again and remeasure, do the same measurement as before. And we found again the anomalies. So the process of filling the voids was not successful because probably the underground water was removing the filling material again. The same we did in my country. So you see the blue line showing negative. It means there is some void also. And I show you what was the void in the center of the big city. So we got a collapse and we found that there is an underground tunnel from the medieval ages. So they had to rebuild everything and correct. This was very important for industry because they were building a tunnel in a sedimentary basin with coal. And we measured just after the front wall of the tunnel when the train goes inside the ground. And we found many negative anomalies, and they were confirmed by shallow drilling. What happened later, they started digging with a big machine from France, and we say, yes, we have to continue with this survey to show you where are the voids. No, it's okay, no problem, we will do the tunnel, no problem. Yes, they continue, and the big machine for 50 million euro collapsed in the hole and it was destroyed. So that was a bad decision from the guys. Another case, if you have an open pit mine, then you have to remove the material, put it somewhere, which is here. And we monitored what is the status of this artificial mountain of the material. And this is gravity per year. So here is the reference starting. The gravity goes down as they removed groundwater from under the body. And then suddenly two profiles showing increase. And they found there is a problem with this system, which was removing water from the body. So they repaired, we continue gravity, and we see three profiles indicating something strange. And what happened then? The mountain of the material start moving and destroyed the factory, as you see. So that was like an industrial catastrophe and economic problem of a large scale. We also measured repeatedly gravity in the deep coal mine at the depths of 1 kilometer. Imagine you go with the gravity meter down to 1 kilometer and repeat it each 3 weeks. And then we also saw increase of gravity, and it was indicating that we get earthquakes or rock bursts. Why? Because the pillars which were left during the coal mining got a high stress, and the stress caused these earthquakes. Another case for a rock search, actually, because the mine which is here in the corner, you can see, they needed a construction stone. How we get it? Yes, we have a small volcano here. So they asked me to do a gravity survey and to try to locate where is the hard rock, because the volcano usually has also a lot of breccia and other stuff. So where is exactly the hard lava so that we can open the digging and get the stone? So we did. It was very difficult, actually. Jungle like in Papua, it was difficult. And what we found a positive gravity anomaly here. This is the residual map, and again a residual map with the horizontal gradients showing the limit of this body. So this was it looks like simple, but it was quite difficult job actually. And the mine was very satisfied that we could locate where is the strong volcanic rock. We also find some magnetic anomaly, and the rock was phonolite, which is a relatively low density volcanics, and there was also a basalt, which we see here in the model. This is totally different place, but a similar problem with the holes, because this is reclaimed land. I think it's Hong Kong, and this is artificial land, and seawater may also remove the sand and causing collapses. So it's another place where the gravity could be applied. This is a survey in the desert. This is survey in the sea, marine gravity. I'm joking, sorry. Because I showed you water, so we can, with gravity, also recognize something about groundwater. This is another coal mine here, and this is normal land with a small town. And the guys decided to test how the hydrogeological system is working. So they did a pumping test in these places. And what we found really negative gravity. Why? Because the water was pumped out from the reservoir, so the pores were dry and the rock was of lower density than the saturated rock. So they decided to give us a much larger monitoring case, also with pumping tests inside the mine. The conditions were very difficult, as you can see. This is the network we did, and this is the pumping borehole topography of the mine with the steps, of course, as it is usual. This is an inverted graph of how they pumped the water. So this is actually the depth of the water, which was down by 10 meters during the pumping. And we found the hydrogeological regime from the negative gravity that there is a channel which is bringing water to the center of the mine and also from the other side. So that was a very important result for the mine because they decided to keep the bottom of the coal seam on place to avoid cutting this reservoir and flooding the whole mine. This is from my city, Prague. This is the castle with the main cathedral in the country. It's this one. So you understand we are going to talk about archaeology. Very detailed microgravity by half a meter station interval inside the cathedral. And what was the target? The archaeologists, they were thinking there must be some unknown tomb of one of the most important kings in our history. And they asked me to do the survey. So I did. I found this red anomaly. We draw how the tomb could look like. And here we see the result. So we made a small drilling with a camera, and actually there were two tombs as indicated from microgravity, and that was actually the discovery of the year 2005 in the Czech Republic. So really important result. We did also archaeology in Egypt. This is Valley of the Kings, which is very famous because of the pharaohs. And we were trying to find some unknown tombs. You see Tutankhamun, very famous tomb and very famous king. And this is another case how we can recognize some structure in the Egypt. But okay, let's go to different topic, geodynamics. We did some surveys for geodynamic reconnaissance, let's say, monitoring different geomechanical processes and also groundwater, as I mentioned already. In my country, we have earthquakes. In one part of the country, we have earthquakes up to 4.5, which is not too much compared to Papua and other places. But we do some repeated measurements in the network. And what we get, these stars indicate earthquake swarms. And you see, there is always some change of gravity. So the gravity is reflecting the change of stress in the underground. There are the swarms here. And actually, what was very interesting that the gravity showed first one direction, like right lateral stress, and then after the earthquake swarms, left lateral, as if it's getting stressed and then repeated backwards. This is very simple model. What could explain this kind of things, like shear stress and change of gravity in the huge volume. We could do something like that somewhere here. Why not, Mr. Richard? So maybe this is one of the famous faults, right? The red one. And I'm sure there are many other important faults which we can recognize from topography. So let's do something together. And we did actually. This is the result of Mr. Leverisa paper. So that's great. You do things like that. So maybe we do something together. This is for you, especially as you are Indonesians. I got a new gravity meter and I decided one day before Christmas, which is critical time, no work, just stay with family, etc. But I decide, okay, I put it in the observatory. So these are the data. This is Earth tides effect, and if I remove, I get the red line. And I got immediately New Zealand earthquake, and then Sumatra, terrible earthquake, which you know pretty well, unfortunately. So what I see in the gravity, I saw just the significant change of the trend of the drift of the gravimeter, and I am totally on the other side of the Earth. So it was global event, the Sumatra earthquake. This is the gravimeter. Okay, I did something similar in Greece also. I will go fast. This is repeated gravity showing that in the southern side of the Gulf, which is a rift structure, it indicated uplift, which is confirmed also by GPS. Here are the earthquakes. And there was another case. I see some stress in the middle. It was a change. Why? And then after a few weeks, earthquake swarm come to this place, and nobody was talking about transform faults. Everybody talking about faults east-west, which are normal faults related to the extension of the Gulf, of the rift. We also recognize by GPS some displacements, and this is one fault, this is second fault, and this is third fault. So this city suffered a lot of earthquakes with casualties. So it's a very important place. This is a very beautiful fault surface, actually. Again, just to show, beautiful country is Greece. I recommend to visit. And this is my monitoring network. One of the stations is here. Is it my end? Not yet. I'm still here. We did something in Egypt similar because there is a significant Kalabsha fault with earthquakes, this one. And here is the high dam. And you know, Aswan Lake is a huge lake, maybe one of the biggest in the world. And if from some reason, like big earthquake, this high dam is broken, you will get, after 1,000 kilometers through the Nile River, you will get 9 meters plus in Cairo, where you have 15 million people, and there would be very, very many casualties. So it's a high risk. So we did something here, but sometimes we don't find the tectonic stress, but we find infiltration of the groundwater through the sandstone from the lake, which is changing the level seasonally. Okay, I have to check the time. Yeah. Okay, we can also monitor fluids in the reservoir. Imagine that you have a reservoir, which is this layer, partly filled by water and partly by gas. And then due to the exploitation of gas, this contact is moving. And you can see the differential gravity curve. So you can actually monitor moving of this gas, which is pushed by water and going to exploitation drilling. This is from Saudi Aramco, some example. From 3,000 meters, I could recognize water flooding case in a big reservoir in Saudi Arabia. Okay, something similar in my country, some modeling, how we can recognize, depending on the depth, depending on the density, how we can recognize what happens with the gas and water in the reservoir. Here, we actually inject gas, and theoretically, you see, the more gas we inject into the water-saturated reservoir, the bigger is the negative anomaly because of the gas. So this could be applied to CO2 or hydrogen storage, for example. Example of something like that from Canada. You see the difficult conditions, but they actually pretty good results. And they could see the bubble of the water extending gas and gas extending oil to the pumping wells. I did one survey in Qatar like that. It was very huge monitoring. This is some theory, but no problem. This is the impact of processing the gas in Qatar. It's not always like this, but the fire is like 40 meters high and the smoke is kilometers high. So they try to re-inject bad gas, and that's why we were doing this monitoring project to avoid this flaring, which is terrible to environment. So it's an environmental issue, actually. Now, I'm sorry you don't see the top, but never mind. Volcanism. I like this topic. Maybe you like it too. Beautiful photo, but a little bit risky for your people. You know, I hope which one is this one in Java. This is not in Indonesia. Another one, we did something in Syria. We found there are many craters, and the local guys were interested in searching where is the chimney of which is bringing magma or eruption to the surface, and why? Because such a place could be interesting for searching for, listen, diamonds. They were expecting diamonds inside the craters. So we could locate this chimney like something like kimberlite, but it was not kimberlite actually. And I think they have never found something like that. We also search for unknown volcanoes. This is example from my country. Nobody know, no geologists know anything about this volcano. So we do geophysics and we find very interesting magnetic anomaly and very interesting gravity anomaly. So I go very fast. It was also not very easy job. We found mushroom. And this is you don't see anything special, but it's a hidden volcano. You see result, gravity, magnetics. This is magnetics, for example, etc. You can play with the data to enhance what you want. I'm not gonna to talk about it. And then we decide for drilling, different conditions. We drilled 85 meters and nothing, just sediments. And then I pray, please give me one more pipe because it was finished. And they gave me one more pipe and we found volcanic rocks because it was a volcanic diatreme. This is eruption? What do you think? Is it eruption? Not really. The car was burned. I'm not gonna to talk about why, but another volcano surge. And now the question for you, what is this? I cannot hear the answers, so I will help you. It's actually Merapi, a painting. So the question is, should we care about volcanoes? And in Indonesia, specifically, you must, because many of them are active. So we should do the monitoring, including microgravity. Why? Because we can recognize the inflation and deflation of the magmatic chamber, which can be also indicated by gravity, repeated gravity. We can see after the eruption or during the eruption some negative gravity indications. I'm not going to explain the details, but we can see a strong signal from volcanoes. This is in Greece. They have also some volcanoes. I'm doing monitoring in Santorini, for example, which is now famous because there was a big earthquake swarm and most of the people was leaving Santorini, and I was going too. So there are some data from 2013, for example, showing here extension of the island because of some rift structures, etc. But here it's more important, it's 23, 24, 25. So two differential maps. And the last one shows maybe some volcano intrusion, some volcanic here, and some other things happening here. I am not going to explain, but it means the volcano monitoring has some meaning. Santorini is a beautiful island, but quite risky. And the swarm was in February 25. I was there with gravity meter. These are the pictures from Merapi because I was in Jogja at UGM University. So Jogja is in high risk. Why? Not only Merapi, which is, as you see, very, very active volcano, looking beautiful now, but looking dangerous here. So that's another point where we should focus with geophysical monitoring, because Jogja has two hazards actually, Marapi, but also this opaque fault, because you remember the big earthquake, 5,000 people died. So Jakarta is very difficult place with a lot of risk. So I have just fast conclusions. I know it was fast, but I wish to present as many applications of gravity as I could. For example, mapping various structures or searching for minerals, hydrocarbons, economical profit, hazard indication of the voids and collapses, then safety in mines, discovery of treasures, stress on faults, volcano monitoring. And I have to comment, and probably Mr. Leverisa will confirm that gravity is needs really accurate work. You have to be patient and perfect, otherwise you don't get some small signals. Another conclusion is gravity is everywhere, so whatever geoscientific problem you have, you should think if gravity could help you. It may look boring, but to me, it's not boring. I like to cover the area with gravity stations and do it. And I want just to repeat, Mr. Leverisa, we have to do it together. That is all. Thank you for listening. I'm happy I did not sleep because here is now almost 2 o'clock a.m. Sorry, I can't hear you. I just catch one word and then nothing and then one word. That's good. That's good.
Oh, it, uh,
Yes, I do.
yep.
Okay, thanks for the question. First of all, yes, you have active faults. We know about it. We dealt with it already. And I think what I saw, even in my country, where the dynamics is much smaller than in Papua, and I could recognize some signal about stress on the fault, uh, I would definitely propose to do it also in Papua. But I can jump to second question. That's extremely difficult. As you saw from Papua New Guinea, which I visited for survey, uh, it's very hard how to find the stations on both sides of the fault, because one side maybe is a valley and you can access, you have maybe even a road, but how to get into the other side is immediately steep slope and jungle. So this is very difficult. And we actually need also the elevation control, because elevation control by long long recording by GPS, but you have to have open space and not jungle. In the jungle is difficult. So these are the difficulties which we would face in Papua. But I think the question is of the logistics, because on one side of the fault it's easy, on one side it's very difficult, and we have to think if we can find reasonable access just to very few points on the other side of the fault, whichever fault it is, but we have to have stations on both sides. So I know it's difficult, but I saw people in Papua New Guinea, they can cut jungle so easy. They are so perfect and so professional. And to build the stairs, as you saw, but it needs some money and some personnel, I know. But I feel it's not impossible, but this is a difficulty. And as what you mentioned at the beginning, that the geology is very spectacular, I would say. So gravity is very good for mapping the geology, because most of the rocks have different densities. So to distinguish and locate the volcanics from granite or from sediments is relatively easy for gravity. But the same problem is how to cover the area if it's jungle, because exploration guys, they have big money to do it, so they can cut those seismic lines or whatever. But for us as academics, this is difficult, so we have to be very careful selecting the target. If you think that one of the faults has some potential that we could actually measure on both sides, and the fault is showing whatever displacement, there is always change of stress. So either it's normal fault, or it is strike slip or shear. Uh, so we could get signal together with seismology, and if we combine more techniques, this would probably contribute to the hazard assessment on the fault. Yeah.
Okay, thank
Terima
you.
kasih everybody
Thank
for
you, Mr.
listening.
Richard Levelisa. Okay. We are limited in time because this
Sure.
seminar will be continued with the other session. So thank you, Mr. Dr. Jan Marlina, for sharing your experience and expertise in this seminar. And we hope that through Richard Lewisa, we will collaborate in the next future to explore using your methods in geophysics in Papua. So,
Inshallah.
inshallah. Okay, so we also thanks to all participants to has enjoyed this seminar. Now I would like to give it back to the main MC, And thank you. Thank you for everyone and enjoy the rest of the seminar.
Thank you very much. Good morning, ladies and gentlemen. Honorable rectors, deans, and all of the leaders in University of Papua. Also, honorable speakers and all of the audience that attends the very important meeting this morning, the first Papua International Conference on Biodiversity, Science, and Technology. Let me share my presentation. Hang on, I will share. Okay. I'm very happy and honored to be here this morning in front of all of the audience, and especially in front of University of Papua staff members and students. University of Papua and IPB University has a very long story in collaboration. I think it was started in 1980, something like that. And I remember that one day I went to Manokwari University. It was a faculty of agriculture of University of Cendrawasih at that time. I am very happy that University of Papua now progressing and advancing a lot. And I hope the advancement is always continue from time to time. Ladies and gentlemen, this morning I would like to share my views about navigating the future of science, technology, and local knowledge to promote conservation, biodiversity, and sustainable development. This is basically a collaborative work between me and my student. Her name is Indah Ratih Rangriani. She's a PhD candidate in statistics and data science at IPB University. And also, she's a staff member of University of Papua. So I think my student Indah Rini Angriani will explore and explain more a lot in her session. As I was introduced, my name is Haidar Anwar Notariputro, and I think everything was introduced by moderator at that time. So first of all, I would like to take the quote written by a mathematician at the University of Cambridge, saying that the future doesn't just happen. We built it with the choices we make today. The better we navigate, the brighter it becomes. So it means that navigating the future is very important for us to have a better future of our life. In this case, of course, what we are talking about navigating the future of science, technology, and local knowledge for conservation and also sustainable development. Navigating the futures mean preparing ourselves to welcome changes, developing curiosity, and choosing to grow free from fear. So you want to grow without fear. That's why navigating the future is very important. And also, due to the global challenges, which are everywhere now, such as climate change, inequality, technological development, navigating the future is very important. Climate change, I think, is very hot issues at this time. Many people talk about climate change, why our climate is changing. In Bogor also face or feel the change of climate. A long time ago, when I was a student, Bogor was very cool, but now become hot, sometimes extremely hot as Jakarta. So it needs an integrated and stable approach to navigate the future. Future navigation is important so that we can participate in determining what will happen. So not just reacting to what will happen. So there is a determination from us when we navigate the future. By understanding trends, anticipating challenges, and being ready for change, then a decision to produce better results for individual and professional and society can be established. This is not only a survival problem, but it is a resilient issues in an uncertain situation. So when we talk about trend, we thought about anticipating challenge. We're not talking about just survival problem, but it is a resilience issues in an uncertainty situation. Of course, our life is full of uncertainty. That is why it's important to understand trend, anticipating challenges, and being ready for challenge. In a world where technology, climate, and global dynamic evolve rapidly, those who can navigate the future hold the keys to innovation, resilience, and leadership. Navigating the future basically consists of four important key elements. The first is science, the second is policy, the fourth is innovation, and the third is innovation, and the fourth is implementation. So not only science is important, but also policy and also innovation. Of course, innovation is a result of research, is a result of science development, which eventually will create a new technology. And then the implementation of this four is important for navigating the future. Science itself plays a key role in understanding environment, identifying solutions for global changes. So we learn science because we know science is important for understanding many things, especially in this case, understanding environment and identify solution for global changes. Through research and development, science could develop new technology, identify solution, and also improve awareness. Develop technology means that science help you to develop technology more efficiently and environmentally friendly. So not only enhance the technology, but also increase the efficiency, and also increase the friendliness to our environment. Identify solution means science helps to identify solutions for global changes. Global change like climate changes, diseases, so many diseases now, new diseases, and inequality. Inequality is very important because for developing countries, usually inequality become higher and higher from time to time. So it needs a solution from science. And then improve awareness means science helps to improve awareness about the importance of sustainability and environmental protection. Through science, we can educate people to understand the importance of sustainability and environmental protection. And also through science, people can do research for the improvement of sustainability and environmental protection in the future. On the other hand, policy plays a key role in implementing solutions developed by science. So when science develop solution, then how to implement it need policy. Through policy, government and other agencies can regulate and supervise, can increase investment, and also can increase or raise awareness. Regulate, supervise mean regulate and supervise the use of technology and resources. Increase investment mean increase investment in research and development, as well as in solution and implementation. So research and development, of course, need to be improved through investment in the future. Increase awareness mean raising awareness of the importance of sustainability and environmental protection. Innovation plays a key role in developing a new and sustainable solution. Through innovation, we can develop new technologies, we can improve efficiency, and we can improve quality of life. Develop new technologies mean develop more efficient, environmentally friendly, and sustainable technology. Improve efficiency mean improve in resource use and waste reduction. So the waste must be reduced from time to time. And improve quality of life. Improve the quality of life by developing better solutions for health, for example, for education, and for environment, especially the emerging of artificial intelligence at that time. In this time, I mean, then the solution for health, education, and environment need artificial intelligence to be involved in developing better solution. For me, for example, I'm an educator, so artificial intelligence for education is very important. Yeah. How teachers can evaluate students using artificial intelligence, and also how students can use artificial intelligence in doing their exercise, their homework, and also their thesis, for example. And that will happen, and we cannot avoid that because the technology is there, and now the technology is improving very fast. The future of science actually derived by several factors, including integration of various methods and technology, the use of artificial intelligence and research, for example, in precision medicine, and also in teaching, I think, is expected to give birth to breakthrough in the next decade. So that the approach can be human-centered approach or interdisciplinary collaboration. Human-centered approach means research to answer global challenges must focus on humans who are affected by the development of science and technology, especially in order to answer the societal problem. Whereas interdisciplinary collaboration, the need for interdisciplinary collaboration will increase, even known as bioconvergence, to obtain solution to the problem of climate change. We are interested in science. There are so many reasons why science is important, because science can predict trend and pattern through data analysis, through modeling and simulation. Data analysis means we have data and we analyze the trend, pattern, and can be predicted using science in various fields, such as trend and pattern in climate change, population growth, technological development, and also, for example, food security. Data analysis is very important. And nowadays, data analysis become a very important area, whereas data science is a new growing field in the world. Modeling and simulation is also important, because before we make a decision, some modeling and simulation sometimes need to be carried out. The simulation means we simulate complex systems, and based on the simulation, we can predict what will behave in the future. Science can develop technology such as renewable energy, disease treatment, and more efficient transportation. Science also increase awareness and understanding through scientific communication and education. And also science face global challenges like climate change, global health, and food issues. Nowadays in academic environment, especially in research environment, there are two cultures that develops during the last 2 decades. It was Leo Bremen from Stanford, who raised this issue that when you are doing research, there are two cultures. The first culture says that you do research by starting from models, starting from hypothesis, and then after you have models and hypothesis, you collect data. Then the data is used to validate your model, is used to validate your hypothesis, and draw conclusion from the results of analysis. That's the first culture. I think that the first culture is very, very usual, and it happened until now. But nowadays, there are the second culture, which is the emerging culture. When you're doing research, you're not starting from model or hypothesis, but you start from data. You have data, and then from the data, you create a model, you create hypothesis, and then you get the answer and can get a conclusion. I think the first culture is the culture is called model-driven. And the second culture is called data-driven. The first culture, the model-driven, was very well known as a research to search. But the second culture, known as to discover. To discover and to search is two different things. When you search, you have a very sound argument. You have a very sound argument. What are you going to find? But in a discovery, you don't have a very sound things to what you're going to find. It's up to the data. What the data say, that's what you find. So that's two different culture in the future. I think the second culture is now growing very well, especially in research. Both the first culture and the second culture depend on digital technology that has evolved very rapidly. In the 2 decades, the digital technology reaching more than 50% of the world population, and it transformed the world society. The technology has become a great equalizer through increased connectivity, financial inclusion, access to global trade, and access to public service. The impact of digital technology that's developed very rapidly is also happen in our work in data science, where mathematical become slowly replaced by digital. So there is a connection between mathematical and digital. And because mathematical usually is very abstract and it's not easy, people tend to move to the digital rather than mathematical. But of course, mathematical cannot be left behind because mathematics is a basic of everything. From talking about from mathematical to digital, there are 3 factors that usually concern us, especially the reality, the culture, and the mindset. So there is mathematical reality and there is a digital reality. There is mathematical culture, also there is digital culture. Mathematical mindset, also there is mathematical mindset. The concept of mathematical reality is very well known, and it suggests that mathematics is not merely a tool for calculation, but the fundamental aspect of universe itself. So mathematical reality means that mathematics is not merely a tool for calculation, but the fundamental aspect of universe itself. Mathematical reality, if we observe carefully, is purely Platonic, intellectual construct. So it's abstraction, it's very high intellectual level. Constructed by intellectual engagement of qualified human participant distributed across space and time. So it is constructed by intellectual engagement. Yeah. So it needs to be intellectual to deal with mathematical reality. Leave a trace in the mind of participant and in journal, article, seminar, presentation. So we talk about mathematical reality in journals, article, and seminar. An individual contribute theorems, derivation, and analysis to involve landscape, article by article. So the contribution is from individual, and sometimes it's very limited because not many people good in mathematics contribute theorem. Mathematical reality cannot be experienced one person, and only a few can participate in it as consumer, let alone contributors. So mathematical reality cannot be experienced one person. Secondly, mathematical reality is unique. There are no competing reality. It's the only mathematics. Mathematical reality is solid, durable, and immutable. Mathematical reality is cumulative. For example, if you compare to geographic territory, except more stable and durable, no continental drift, no earthquake, no sea level rising, no weather-induced erosion. So it's very stable. Mathematical reality is very stable. Yeah, it's very stable. On the other hand, digital reality is purely tangible. You can see, you can try, and everything. And an evolving web of information technology, resources distributed across internet, embodied by URLs pushing data and services, bewildering variety of contribution possible far beyond academia or science. So sometimes everybody, most of people can contribute to the digital reality. Digital reality cannot be fully experienced, but any specific element of digital reality may be checkable by pinging URLs. Almost anyone can participate as a consumer or even contributors. This is very different from mathematical reality. And also digital quality is not really unique, but it's quite unique. Within one nation, internet, there are no competing realities. Digital reality is active, changing from time to time very fast. Whole island in this landscape can spring almost from nowhere. Like, for example, what we are doing now. We are doing a conference. I am from Bogor, some people from other country, etc. And whole island is a reality can be effectively forgotten. An entire continent of reality can be rewritten in few years. Now, integrating local knowledge and scientific knowledge. Integrating indigenous and local knowledge in conservation and natural resource management initiative is necessary to achieve sustainability, equity, and responsiveness to local realities and needs. Knowledge integration is the starting point for converging different systems and enabling knowledge co-production. So, knowledge integration is very important. How to integrate the local and scientific knowledge. We don't need to contrast the local and scientific knowledge, but it should be integrated. Why integrating knowledge is important? Yes, it's very important because it inspires intuition for pursuing knowledge of integration process. Knowledge gap for integration are twofold. The first is limited empirical evidence. We have a very limited empirical evidence about the integration of knowledge gap. The lack of documented cases of negative impact of knowledge integration is also very limited. So we need more understanding about the gap of integration. And also we need to document more cases where the gap of integration can be integrated. Research has demonstrated, this is a good example, that forest loss rate is significantly lower within indigenous people land, yet indigenous people right within such land are often still not recognized. I think also in developing countries, usually we can see that indigenous people are right often still not recognized. Although the facts show that the indigenous people can manage better, more sustainable than new technology. Balancing and respecting different knowledge system is pivotal to enhancing decision-making process in conservation in natural resource management research project. Integrating indigenous knowledge with modern technology for sustainability is very important. Sustainability are critical to preserving ecological balance and ensuring the long-term health of our planet. Integrating indigenous knowledge with modern technologies offer a unique and powerful approach to achieving this goal. For example, when it combined with contemporary technological advancements such as GIS, remote sensing, and data analytics, this integration has potential to enhance management practices, promote environmental sustainability, and support community resilience. So, indigenous knowledge need to be integrated with a new technology to enhance management practices, to promote potential environmental sustainability, and to support community resilience. And at the end, we need to promote conservation and biodiversity. Conservation and biodiversity are essential for ecosystem services, for health and well-being, for food security, for climate regulation, and for genetic diversity. For ecosystem services, for example, conservation and biodiversity can provide clean air, water, and fertile soil, which are crucial for human well-being and health. Whereas health and well-being mean that healthy ecosystems support human health by regulating diseases and stabilizing the climate. Food security, which is one of my students now analyzing in Papua, is also a result of promoting conservation and biodiversity. Whereas biodiversity is crucial for food security as it supports the production of crop and the pollination of plants. Climate regulation means that biodiversity has important role in forests absorbing amount of carbon dioxide for climate mitigation. And genetic diversity means conservation of biodiversity is important to maintain genetic diversity, which is necessary for their ability to adapt environmental changes. Now I would like to present an illustrative example of how science, especially data science, can be used to model the security data in bird head seascape of Papua. This is a navigating of science to be able to be used in biodiversity and sustainability, especially through the illustration of food security issues in Papua. Most districts in this region are the category of very vulnerable to bit of food insecurity. Some of the districts are marine conservation areas, which are divided into several areas known as bird headscape. So the areas is in Papua, yeah, it's in especially in the bird heads seascape of Papua, but sometimes there is somewhere in Manokwari here, I think. Food insecurity cannot be measured directly, but usually we use several dimensions. This means that food security is latent. Latent meaning we cannot measure. The measurement of which is suspected through several indicators. In statistical point of view, this needs to be modeled through factor analysis. The excess can be used to measure food insecurity. It means that food insecurity may occur due to limited access of household to buy food. Moreover, since the indicator used is binary in this research, then we use the trachoric correlation to measure the correlation between one variable and one indicator and other indicator. This is not ordinary correlation, but tetrachoric. The model that we use by Angriani, 2025, is DWLS, standing for diagonally weighted least square, to estimate parameters in factor analysis if the indicator used is categorical. The weight used, because there is a weight here, are derived from diagonal element of the asymptotic covariant matrix. The diagonal element is very easy, it's much easier, especially when you invert matrix. So this is a kind of approximation. When you have a full matrix with a very big dimension and with sparse inside, then sometimes the diagonal element is important. Okay, I will, after this is finished, the data collected from socioeconomic survey, and then the results here, I just want to share here. We show through box plot of food security score, in which 2010 and 2012, the score is very low here, mean security, a good security. And in 2021, 2025 is much lower again, which is mean food security in the six area getting better. So there were discrepancies of food security, but it is apparent that the food security status was better from time to time. The last I want to say some concluding remark. The first is science and technology is very important to enhance our everyday life, to advance critical field, and to drive economic and societal progress. The second is indigenous knowledge is very important, especially for environmentally sustainability, offering solutions for conservation, resource management, and climate change adaptation. So it is our responsibility to navigate the future of science, technology, and indigenous knowledge for promoting conservation, biodiversity, and sustainable development through education, research, and development. I think that's all. Thank you very much for your attention, and have a nice day. So I stop my... Sorry, I cannot get your your question because the sound is not that good. Can you just say in one word, for example, the question?
Can we teach students to learn about machine learning, but they don't have not much knowledge in statistical mathematics, something like that?
Okay. So statistical machine learning basically is a machine learning when combined with statistics. What does it mean? Machine learning is an algorithm to provide solution, especially for complex system, not a simple system. Like for example, if there is non-linearity, there is a lot of interaction, there is so many multiple linearity and whatever. And then sometimes people from other field just take for granted that everything will be okay when using machine learning. But in our research in Bogor, there are many examples. Well, if machine learning all alone we use, the result is not optimal. We need to explore what kind of problem, especially from in point of view of statistical problem, rather than only data, only numbers. But statistics will learn about the trend, the pattern, the assumption, the uncertainty, and everything. If this thing is included in the model, then we will have a better solution rather than just leaving this thing out. That's I think. So what you need to learn? You need to learn statistics, you need to learn mathematics, and you need to learn computing. That three aspects need to be learned by student to understand the statistical machine learning. That I think my answer. Thank you. You are welcome. Okay, thank you. So what should I do? Okay, you're welcome. Okay, thank you very much. Okay, let me leave the session and selamat siang di Papua.
Yes, I can. Test sound. Once again, thanks. Oh, okay, baik. Okay, selamat siang, everybody, distinguished guests, respected speakers, and all the participants of the first Papua International Conference on Biodiversity. And it's a welcome all of you to this exciting science gathering. My name is I am from Universitas Cendrawasih Jayapura, and I will be serving you as your moderator for consecutive invited speaker sessions this morning. Before we begin, please allow me to express my apologies that I am only able to join and moderate this session online and not together with you on site in Manokwari. But however, I am truly delighted to be the part of this important conference and to share this inspiring moment with you all virtually. In this session, we are honored to have Dr. Scott Alexander Hocknull, as you can see on the screen. Dr. Scott Alexander Hocknull is a professional paleontologist with 34 years of experience. Wow, it's really a pleasure to have moderate your session. This session entitled Quaternary Connections and Extinctions, the Rare but Shared Vertebrates from Sundaland, Wallacea, and Sahu. I will not delay anymore. I encourage you all participants to stay engaged and prepare your questions for this discussion following the presentation. So without further delay, please join me in warmly welcoming Dr. Scott Alexander Hocknull to deliver his presentations. Please give him our best applause. Dr. Hocknull, are you ready? Yes, yeah, you are ready. So
yes, I am.
The
Thank
floor
you.
is
Can
yours.
thank you. And
Yes,
am I audible?
Hear you. Yes.
Excellent. All right. Well, I will share my screen. And go. Can you see my presentation? Excellent. Okay, well, Salamat Pagi, very happy to be here. Thank you very much for the invitation. I'm very excited to speak to you today, all the way from sunny Brisbane, Queensland, where it's quite hot, but very much connected to where you are in Papua. I've always been interested in the region, and as Professor Tim Flannery was talking about yesterday, he set up my talk quite nicely, because what we're going to be talking about today is this shared relationship that we have through fossils and through biodiversity. And of course, there's a lot of really interesting things that we can learn about what our past was and how that is shared today. So yes, I'm speaking on behalf of Central Queensland University. I just moved over to the university from the Queensland Museum. So I've had many years of experience in both Australian and international paleontology, from dinosaurs all the way through to the small animals that Professor Flannery was talking about. So you'll get to see a little bit of that as we go along. I'd first like to acknowledge the traditional owners of the country I'm sitting on. This is the Gabi Gabi and Wini people, and Turrbal. Also, I'd like to acknowledge all of the traditional owners from the sites where we find fossils in Queensland, and in particular, some of the sites that we're going to be talking about. So I'd like to pay my respects to them, past, present, and future, and emerging. So when we move into thinking about why on earth some guy in Queensland is talking to you guys up there, and why are we talking fossils, we actually have a shared connection that's hundreds of millions of years old. So I'd like to say that we've always been family and not actually neighbors. If you look at the diagrams here, these are ancient paleogeographical globes, so reconstructions of what the world looked like as far as we can tell, going back 115 million years in the top left corner, all the way through to the last 100,000 years in the bottom right. Now, the yellow star is essentially where you guys are now in West Papua and the Vogelkop, and the blue is where I am in Queensland. But what's really interesting is when we go through time, so from left to right, from 115 to 49 to 20 to 4 million to 1 million and to the last few 100,000 years, we've always stayed connected. And what's really interesting is we've stayed connected, but that connection has actually come from a very southern position. So unlike where we are now, right on the equator and sharing northern southern hemisphere, we actually had our origins back in Antarctica. It's quite mind-blowing to think. So what that means is our shared heritage actually goes back to the time of the dinosaurs. And so this image here is a reconstruction that I did with some paleo artists about some of the dinosaurs that were found in Queensland and in Australia, including meat-eating dinosaurs, things called megaraptoran theropod dinosaurs, long-necked sauropod dinosaurs, and some of the largest in the world. In fact, the fellow in the background there, Australotitan, is one of the largest dinosaurs ever found in the world, shares a very similar history and size to some of the dinosaurs we find in Argentina. But what's really interesting about this story is there's an assumption that because we were down the base of the globe around Antarctica, and Antarctica was connected to South America and India and these sorts of places in Gondwana, that they all share relationship. And it's kind of weird though, because when you look at the evolutionary relationships of some of these big extinct animals, so for example, we have the megaraptorans, these nasty looking dinosaurs with big teeth, huge claws, they actually have a peculiar history. So the earliest forms come from the Northern Hemisphere, from Japan and Thailand and Southeast Asia. Then the next group actually comes from Australia, so within that evolutionary tree, so they split off. And then the next group actually comes from South America. So if you look at that family tree, yes, the Australian species share something with South America, but what's really interesting is the ancestors are from sort of the Northern Hemisphere, Southeast Asia. So the question then is, well, how did those ancestors get to Australia? So there's only two ways you can do it. You can either go all the way around through the entire globe, all the way through South America, and then into Australia. But then that would mean that you would have ancestors in South America as well. So what this suggests to me, and it's quite a controversial suggestion, but there's this potential shared fauna that crosses all of the continental pieces that now make up Indonesia. Including West Papua, including the Vogelkop, which was there at the time, and a lot of pieces that end up making up Sumatra, Borneo, Sulawesi, all those areas that, you know, combine to make the archipelago. Unfortunately, it's a very active area, as Tim was talking about yesterday, so the rocks are difficult to find, but wouldn't it be awesome if you guys could find the first dinosaurs from Indonesia in this period? I'm sure they're probably out there. It's just they're going to be very difficult to find. But think about the sort of animal you might find. If we go to the sauropod dinosaurs, these gigantic long-necked plant-eating dinosaurs, and we're looking at an evolutionary diagram there on the left, this story is almost exactly the same. We have ancestors that are either Australian or they're from Asia. So we have Asian ancestors, we have Australian descendants, and then we have South American sauropods all mixed up in the middle. So it suggests that there's this sort of weird interchange. Now, at the moment, everyone's focused on that southern interchange, that everything happened between South America and Australia, and that for anything from Asia, it has to go all the long way around. It doesn't seem to drop off any friends on the way. So again, what about this potential for crossing land bridges or crossing sea gaps and so on that lots of animals do today and still do today? So it seems to be a trend that's been going on for millions and millions of years. But of course, without a fossil record, you can't put that in the hypotheses because you can't really test it because there's nothing there. So again, wouldn't it be cool if you found a gigantic sauropod dinosaur somewhere in Indonesia? It gets even more interesting when we start looking at the non-dinosaur areas, and we're talking about lizards now. Now, we all know the fellow on the right here, Komodo dragon, Varanus komodoensis, found on the Komodo Islands and Flores in Indonesia. A very amazing, intimidating animal, but very cool. Now, you might be interested to know that I worked on fossils of this animal from Australia at about 4.5 million years ago. So this animal was in Australia, had its origins on mainland Australia, and has been found on the islands to the west, which I'll get to in a minute. On the left, you'll see what we call agamid lizards, or another group of dragons. And you see the Chinese water dragon, or the Southeast Asian water dragon in the top left, this beautiful green animal. In the top right is the Australian water dragon. And the bottom left are the Papuan and Indonesian dragons, one of them, that shares a relationship with all three. They all look very similar. And then you've got this weird one on the bottom right, which is called Moloch, or the thorny devil. And it's found in Central Australian arid zone. And what's really crazy is that it shares a closer relationship with these three than it does any of the other Australian dragons. It's a very peculiar story. So if we look at the evolutionary diagrams, and again, we don't have a lot of fossil records, but these are genetic molecular evolutionary diagrams that show what groups are related to what. And using molecular clocks, we can come up with a general idea of when these huge lineages divided. But what we see is interesting. So if we look at the top diagram, which is all of these sorts of lizards found worldwide, you can see that there are a whole bunch of them that we all find in this region that actually were related to one another and connected to one another about 120 to about 100 million years ago. That's interesting because that's exactly the same time as the dinosaurs that we were talking about. So for some reason, we have this relationship of Australian, Southeast Asian, Indonesian lizards, the gamete lizards, these little tiny dragons in this region, splitting off and diversifying right at the same time as those dinosaurs that we look at. So even though their descendants are living today and the dinosaurs aren't, from that period anyway, we've got these lineages that still exist. So that's really interesting. But when you drill down into one group, which is the amphibiolurines and the hydrosaurines, so the Hydrosaurus dragons, I'm sure you've probably even seen, they're fantastic in zoos. But the group that we're talking about is the amphibiolurines. You have, this is supposed to be, the amphibiolurines are supposed to be all Australian, Australopapuan, but there we have Physognathus cocincinus, the top one, which is the Chinese water dragon or the Southeast Asian water dragon. So all of the ones in that main central area are shared between Papua and Australia. And then this guy, out of nowhere, just sort of ends up in the middle of nowhere and has this weird juxtaposition. So it's quite clear that that basically there's this interchange that isn't really working well. So, but where are the fossils? It's like finding a needle in a haystack. But we have found fossils, and we found them in Australia. This is Riversley. So this is in far northwestern Queensland. It's a beautiful place, very, very arid, lots of limestone rocks, very similar to the limestone that you find in your part of the world. And there are beautiful fossils found in those caves that are up to 15 to 20 million years old. And these fossils on the left represent the jawbones and teeth of totally new dragons that have that deep relationship. So we know that they were here. Now, were they in Indonesia? They have to have been because all of the families are locked up in that area, but we have absolutely zero fossil record. If we look at going back to the other dragons, like the Komodo dragon and the lace monitor, they've got an even more peculiar story because most of their radiations are occurring all through this region. So if we look specifically at just one little group, this is the Komodo dragon group, we actually find that even just this one group has some weird relationships. We have Varanus varius, which is the lace monitor in blue. That's an East Coast dragon, basically East Coast goanna in Australia. And then inside that, nested inside that, is the Komodo dragon and two extinct species. One is Megalania, the giant goanna from Australia that got to 6 meters long. And the other one is a new species that has been found as fossils in Timor. And Timor is really interesting because it has some very, very old fossil material, not easy to identify. Now, what's really interesting is you have the Salvador, the crocodile monitor, and that's also found in Papua and New Guinea. And it's very, very interesting and a peculiar animal. So this whole group shares this relationship between Indonesia and Australia through Papua. So there's a lot of missing parts of that record. So what's interesting, though, is that their ancestors are found as fossils in Australia, and they go west and become settled in many, many parts of the Indonesian archipelago. In fact, they get as far as Sumatra and Java. So it's really interesting. Why did they get there but not continue? Or did they get there and go extinct? We don't really know. This secondary size species gets to Timor, doesn't get any further, it seems, but maybe it does. We don't have the fossil record. And Megalania only found on mainland Australia, but we know that mainland Australia was attached to the whole of Papua New Guinea and the whole of New Guinea through hundreds of thousands of years, millions of years. And we know, as Tim was saying, that the Vogelkopf's been around for ages. So wouldn't it be cool if you found the fossils of a 6 meter long goanna living on the islands and in the Vogelkop? This is what to look for. Komodo fossils. So on the left-hand side, we have the Komodo dragon fossils from Australia and a Komodo dragon skull from Flores in the middle, bits and pieces of the skeleton. You can see in the middle photo, we've got a Komodo dragon skull at the bottom, and then the skull of a reconstructed Varanus priscus called Megalania. The one behind is gigantic and enormous and completely overestimated, but that's an example of how paleontology changes time. Yes, this animal was way too big, the big reconstruction in the back, but still, Megalania was at least twice, 3 times the size of a Komodo. And we know that the Komodos were living in Australia up to 4.5 million years ago, perhaps more, alongside all of these weird creatures. So we think of Komodo dragons as being an island giant that sort of made, might have arrived as a small lizard and started eating animals and got bigger and bigger, but in fact it didn't. It arrived already big because it had honed all of its skills on mainland Australia, eating these really weird megafauna. So over time, I've been taking the pieces and reconstructing what this animal looked like, both Megalania and the Komodo dragon. And here's pride and joy for me is the reconstruction of this gigantic animal living in Australia at full size. So this is a 3D printed out, 3D digital sculpt of Megalania that was based on the fossil bones that we digitally sculpted, colored, and then 3D printed out and placed in front of a fantastic animation. So if you're ever in Brisbane and you want to have a chat, let me know and I can take you for a tour. Now, the really interesting linkage, and the one specifically to the Vogelkop, and this is really a connection to the relationship that Tim and I have. When I found these fossils at Mount Etna, which is in central Queensland, in this mine, so this is a limestone mine, you've got these caves in limestone in the center there. There's me sitting on some limestone looking for fossils. I found this little jawbone. So the little top jawbone here is very interesting because it's a little possum. It's a little tiny ringtail possum, and the jawbone it's next to is from a museum specimen that was collected in the Vogelkop some decades ago. And it's identical. It's just broken at the front here, but the rest of the jaw is identical. And it's from a particular ringtail possum, a little pygmy ringtail possum. Tim showed some video of these little pygmy ringtail possums. There's a number in the highlands and in the Vogelkop. So we're not exactly sure what species of what, but they're all there and they're very closely related. To give you an idea of how different these areas are today, Mount Etna Caves and Capricorn Caves are where the fossils I'm talking about now are coming from. And Ayamaru Lakes are where some fossils that started the process of discovering the living animals that Tim talked about yesterday. What's really cool is that there's more than that. So when we look at the fossil record of Mount Etna and Capricorn Caves, we have everything from giant blue tongues like Teliqua gigas, which also occurs in the region. We have Komodo dragons that occur certainly in the islands, but haven't yet been found in the Vogelkop. Maybe they will. We have a dwarf cassowary, and you also have one. There's all these sorts of bandicoots, cuscusses, tree kangaroos, those possums that have been discovered living as Lazarus taxa up in the Vogelkop. Here we have very similar species, if not the same, as fossils in Mount Etna and Capricorn Caves in Queensland. The woolly ringtail possums are the same. The little tiny dwarf ringtail possums are the same. Even that cute little Camboya specimen, we've got something that's absolutely identical. So cool that they look exactly the same. We have little tree rats and we have giant rats, tree rats as well, all sharing the same, almost identical shape, form, species as the ones that were found in the Vogelkop. So this is really interesting. But here's the cool thing. In Mount Etna and Capricorn Caves, we also have megafauna, and we have all this range of fossils. So we can reconstruct a rainforest that was existing in the time around about, and it existed for several hundreds of thousands of years, from about 500,000 years ago to about, 90,000 years ago is the youngest we have so far. What's really interesting is when you start looking at all these animals, think of this not as Australia, but as Papua, West Papua. Think of this as what might have been living in your country tens of thousands of years ago, or even very, very recently. Giant snakes, giant ringtail possums, even the thylacine, the Tasmanian tiger. We had giant frogs, these gigantic, massive frogs that were the size of footballs, Komodo dragons, and of course our little possums, and the extinct megafauna species of kangaroos and diprotodontids that Isaac and Jacob were talking about. Little itty bitty tiny frogs, ghost bats, which we have here in Queensland, are shared again within a family called Megadermatidae. They're shared with Southeast Asia and Indonesia, so it's quite likely that we'll find fossils there. These peculiar marsupial lions called Thylacoleo. Even koalas, wouldn't it be cool if you found a fossil koala for the first time? That would be pretty amazing. So there's a lot that can potentially be found in the fossils in Papua, in New Guinea as a whole, but certainly in the Volgocop because it's so ancient and so old. What's interesting though is that when you think about, well, why are they here in Queensland or in the east coast of Queensland at Rockhampton and all the way up in Papua and not anywhere in between? And it's kind of interesting because when you look at the fossil record at Mount Etna, when we look at the teeth and we look at the different creatures, what we're finding is that they're almost all New Guinean in some way. So for example, when we look at the tree kangaroos, we find fossils of animals that are found only in New Guinea now, but also we don't find fossils of animals that are found in the wet tropics of Australia now. So for some reason, this connection between East Coast Australia and New Guinea kind of bypassed the rainforests in the wet tropics. Very strange. Either they were there and they were dropped off and they've all gone extinct, or they just didn't get there in the first place. Peculiar. But it repeats itself time and time again. When you look at the evolutionary, these are the relationships of those cute little ringtail possums. Again, we have the weird one that has been discovered now in the Volgocop living. And we have the little pygmy ringtail possums, all from New Guinea. And we have even parts of the lineage that are from New Guinea, the woolly ringtails. But the ones that are crossed out here, the ones that we don't find in the fossil record, are all from Australia. It's really weird. We can see that in the pygmy possums as well. All of the lineages of the pygmy possums that are in Australia are not found at Mount Etna and Capricorn Caves in Queensland, but the one that is found in New Guinea. So it's pretty cool. So how do we figure out why this is the case? Well, I'm going to pull some really interesting information about human evolution and population sort of dispersal and concepts of how people arrived into the Sahol, Australo-Papuan region, and how they may have moved through the continent. And there's some great stuff. You can look at the topography of the environment. It won't have changed a huge amount in a few 100,000 years, relatively speaking. There was giant lakes and all sorts of rivers and things. So these researchers did some fantastic work of mapping out, for example, slope and aspect, and trying to find basically the path of least resistance of humans coming into the continent. But humans and possums are kind of one and the same in that humans move through forests, possums like to move through forests as well. So these sorts of animals may share a similar path of least resistance. They certainly aren't going to bother going over hard terrain to get through, just like people wouldn't. So what's interesting is when you look at the slope index, which is most of the lowest areas are in very, very deep blue, which is ironically most of Australia. But if we go back, you can see a very low area here in the Volgocop, and that connects up through lower sea level all the way up along the east coast of Australia. So it's actually not that inconceivable to see that just the slope, just the fact that it's flat and they don't have to go over hills, means that they could get to Australia. What it also means is that they miss the highlands up here in Australia, in the wet tropics, where those species that we don't find in the fossil record exist. So that's really interesting. If we look at the pathways or the probabilities that what they call the superhighways, the corridors for human maneuvering across the continent, there's lots of different places sort of crisscrossing the continent as predictions. So here we have the grey lines, the suggested area for movement of people across the continent. And what's interesting is when they arrive in the Volgocop, they go right through down the base of the highlands, then across and then into eastern Australia. For some reason, they go on the western side of the Great Dividing Range or of the highlands, but they could just as easily have popped over and walked down the coast. So for the possums and the fauna, makes it very simple case for, well, there's a path of least resistance as well for the best corridors of habitat and places for dispersal. And again, it misses all the areas where the animals that we don't get in the fossil record actually exist today. So that's really cool. We have this shared relationship. But why are they only found in New Guinea now and in the Vogelkop living and have gone extinct, it would seem, in Australia? Well, when you look at a global context of where Australia is in New Guinea, it sits in the Pacific, and the Pacific has had a significant amount of upheaval over the last several hundreds of thousands of years. Now, I'm going to show you a bunch of data. Don't worry about it. They're just wobbles and they're just little graphs. But what it shows is that around 280 to 270,000 years ago, there was a complete climatic shift. So we went from dominant La Nina conditions to dominant El Nino conditions. We all hear those names, but basically El Nino or La Nina is relatively good for us. El Nino is not. So what happens when you look at the records across the globe is that there are drying events, less humid events, complete El Nino state. The East Australian current brings less water to the coast, and hidden up in here in the Vogelkop is a little enclave of area that's not really being affected, as we can see. And right through this period of time, we have increased seasonality. So imagine you've got a rainforest that needs water all year round. Then suddenly it becomes very seasonal. You lose all that rain, goes into big droughts. That's not great for rainforest. But what's interesting at this period of time, there's a double jump where everything goes quite disastrous for the Australian continent. But again, the West Papuan area is probably protected. What happens to Australia? Well, it goes arid. So when we look at the species at Mount Etna and Capricorn Caves after that rainforest area where everything seems to go extinct, it's replaced by arid zone species. This up at the top right is a bilby that we find in the arid zone of Australia. Tassie devils, all sorts of arid zone species, diprotodons, things that are found mostly in open habitats. We even have the arrival of rats and mice and a whole bunch of other weird animals that come into this environment. But we do have, you know, a few hold-ons. So we have like one bone of a tree kangaroo, sort of must have been living in a refuge. So to sum up, we've got a lot in common. We really are a collaborative entity. We are a family. We're not neighbors. And there are so many potentials in West Papua for the whole and the whole Papuan region for fossils of this era, from dinosaurs all the way through to the Pleistocene. It's very difficult. It is very rugged. And there's been lots of opportunity, but not really anything has been discovered. But we need people on the ground like yourselves. And what happens when this happens in Australia is we work with communities, traditional owners, local communities, to build tourism. And paleotourism, which is my new role at Central Queensland Uni, applied paleontology, basically using the fossil record to look at the past, to understand how the environments have changed and whether we can use it as a baseline for future prediction. And paleotourism, taking those fossils, taking that experience, taking all those cool animals of our past and presenting them back to the public in entrepreneurial ways that can bring in socioeconomic benefit for community, but also connect traditional owners back to their country, or connect stories that they have of all of these animals, as Tim was talking about, the traditional owners across the areas where these new mammals have been found, already knew about them, already had spirit and sacredness to them. And that's fantastic because it draws a line between science and traditional knowledge and traditional understanding, which is excellent and brings us all together as one people. So thank you very much. I'd like to acknowledge these people. And if you do wish to collaborate, I'm very much happy to chat. Thank you very much.
Thank you very much, Dr. Hokno, for your very fascinating presentation. So I believe we still have 3 minutes for Q&A time. So maybe one question from the on-site from Manokwari, and one questions. Mr. Priyambodo already raised hands, so I have to give time for him. So one question from Priyambodo, Mr. Priyambodo, and maybe one more questions later from the on-site if there's any applicable. So please, Mr. Priyambodo, you have your time. Your sounds, please unmute first. Okay. Okay.
Okay. Okay, thank you for the time. Hello, Scott. My name is Priyambodo from University of Lampung. Thank you for your presentation. My questions, considering the rapid environment and climatic changes we face today, what kind of lessons we can learn from the quaternary extinction and some kind of dispersal patterns to help predict or some kind of mitigate the biodiversity loss in this era? Thank you.
Thank you. That's a fantastic question. Yes, the key thing about paleontology and why, who cares about fossils? I mean, will they help us in the future? Is baselining. So to give us an understanding of what the environment and how it functioned prior to any disturbance. So that's your first step. We want to know if we're going to conserve an environment, if we're going to protect an environment, if we're going to help biodiversity adapt to changes, we need to know where we're actually wanting to go. So that's one thing. On the flip side, if the projected global warming predictions are such that there's an actual change, a complete change in the environment, we need to know how those animals adapted to changes in the past so that we can figure out, well, are they winners? Are they losers? What happens within their environment? Now, just looking at fossils by themselves is one thing. You can put a name on them and you can say, oh, that's a species X, that's a species Y, and that's very nice. But what we're doing is we're moving well and truly in a new direction, which is taking those same fossils and applying geochemical techniques, biochemical techniques, microscanning, basically to characterize the animal as an individual. So if you think about a single possum tooth, we can look at strontium, and strontium will tell us where it lived in the environment. We can look at calcium, we can tell what sort of plants it was eating, carbon the same, oxygen for rainfall, hydrogen for many different aspects of dispersal. And so we can start building a picture of the entire environment from an individual's basis. So if you think about these fossil records in the Quaternary, especially in caves, because there's lots of owls and bats and things, and these caves are like pit traps that the zoologists dream. They're like, they've been doing this for thousands of years. They've been collecting the environment. So being able to take that knowledge and then figure out what has been going on. So yes, the rapid climatic changes that occurred 280,000 years ago show some significant changes in faunal species. But what's interesting is it didn't necessarily say that they went extinct. It just said that they were restricted, and they're restricted to particular refugia. Now, we don't know where those refugia are just based on some fossils, but if you can find in the strontium where all of those animals used to live in the environment, you can actually pinpoint where the refuge was and then protect that area, because then you know that when climates change, that refuge is a natural, it could be hydroclimatically a refuge. It might be a spring, it might be a whole bunch of different things that you haven't thought about, but the fossils can say, look there and protect that area. Thank you.
Wow, interesting. And maybe one more question from the on-site, if there's any. Okay. Maybe also last questions from online, Mr. Marcus, the Dean. So the time is yours. Maybe one last minute before we close these sessions. Yeah.
Okay. All right. Thank you, Scott. Nice to meet you, and very good presentation. I just want to confirm my question to Tim yesterday. So the missing puzzle here that we have to confirm your hypothesis that in the past we have the connection between Australia and also with focal cope is the fossil mammals, right? Particularly the dinosaurs. And I'm not sure with our current here in Papua, especially the focal cope area, we have a mining like the cement factory. And then at the moment they operated in the limestone mountains. And then let's say that the prediction that they will still operate it for 20 or 30 years after they digging all the limestone, then perhaps we can end up find some fossil.
Yeah,
But
that's
yeah,
Marcus, thank you. Yeah, in fact, all of the majority of the fossils that come from Mount Etna were discovered through limestone mining.
okay.
So and what happened was I worked with the mines to go, look, the limestone is what you're after. That's not what we're after. We're after the clays and the sediment and the material that's infilled all the holes. And they actually don't want that. It's hard for their lime kilns. So what they do is they usually dig it out and they put it somewhere to serve as for revegetation. But what you'll do is you'll find that there's tons of bones in those sediments that have infilled the caves. So what I'd worked with the mine was just to go, look, I don't want to stop the mining. I'm not going to stop you from doing your work because that creates tension. What we could do is we can take that, set it aside somewhere so it's safe and accessible. Now it's a huge citizen science program. Now we have kids from schools that sift through and look for all the fossils and bones. So you can take a resource that is going to be destroyed, there's no way to stop that, and actually transfer it over to become a scientifically valuable, community connected, tourism related benefit. And that's what we've seen. And so, yes, I 100% believe that any mining, whatever units they're cutting through, it's just about having the eyes on the ground to go, actually, when you find a fossil, don't freak out and don't like bury it or move it aside and go, oh, it's all going to be stopped. It's actually go, let's just talk about moving that layer somewhere and having people access it. And then suddenly you have a whole industry.
Okay. Thank you. Thank you, Scott.
Thank you.
Once again, thank you very much, Dr. Scott Alexander Hocknell, for your fascinating and insightful presentations. And let's give us our best applause for him, ladies and gentlemen. And on behalf of the organizing committee, we truly appreciate your contribution to the conference and your willingness to share your such valuable knowledge with us today. So here is the certificate of appreciation. So thank you so much, Dr. Hocknell. So now, ladies and gentlemen, as we conclude this session, it is my pleasure. We would like to go to the next sessions. You already joined with us, Dr. Marcus Herianto Langsa, the Dean of the Faculty of Mathematics and Natural Science, Universitas Papua, UNIPA. So Dr. Langsa has an impressive research record in the field of chemistry, particularly in environmental science, as we can notice his questions to Scott previously. So, and he already has been actively contributing to advancing scientific research and education in Papua. So today, sorry, Dr. Langsa will give us our presentation, so I will not stay delay any further. But Dr. Langsa, we already have delay like 20 minutes, so maybe this session we can wrap up a little bit so the later sessions can still have their track time. So the floor is yours, please, Dr. Langsa.
Yeah, thank you so much for this opportunity. Because you already remind me about the time limit, and I'll try to finish my presentation in I hope maybe 10 minutes. If that's okay.
Thank you so much.
Yeah, so the topic for my presentation is about the drinking water as a guaranteed commodity. The option is we have oxidation and also the disinfection. I will make it quick. I will skip some slides that not really, well, actually they are relevant, but because of the time limit, so I will focus on the main topic that I will discuss for this morning. So the main issue that we have now in any place in the world is wastewater. So whatever the strategy, the technology, the policy, the regulation that we have, at the end, we will always end up with the production of wastewater. Drinking water will be transformed at the end into the wastewater, whether it is in the form of black water, green water, or any kind of wastewater. So when we talk about wastewater, we will need to look back in the history, especially during the Industrial Revolution era. Started in 1750. At that time, we have increase of population, and the side effect of this kind of increase of population is the massive pollution on the surface water. As we can see from the graph here, the number of typhoid cases started in 1885 since they discovery this kind of waterborne disease. We find that the number of the typhoid cases is already like more than 1,000 in 100,000 of the population. This is the case in USA. And then when we see the graph here, after the next 20 years, the number of the typhoid case constantly increase. And then in 1996, they find the filtration, one of the very old treatment process, the conventional one. But then we also find that decrease in the number of the typhoid cases. But then if we compare the cases with the 20 years ago, looks like the number is still up to the 1,000 cases per 100,000 population. And then the story is slightly different when they discover the disinfectant. One of the disinfectant they used at that moment was chlorine. And then we can see the rapid changes in number of the typhoid cases after 1930 or the discovery of the process for the chlorination. So again, at that time, we success to defeat the waterborne disease caused by bacteria and all kind of the pathogens. The combination between filtration and also the chlorination successfully remove all the waterborne disease. Especially in this case, we see in early 20th century, starting in 1900 and to 1940, we can see the number of the disease caused by waterborne disease getting low. But then it's not really happened too much. 60 years after that, this gentleman, this guy, Roop, he found that the treated water, especially the chlorinated water, in comparison with untreated water, produce what we call now disinfectant or disinfection byproduct. So Roop published his discovery in 1974 in Water Treatment and Examination Journal, and this has changed the world perception about the use of the disinfectant byproduct. So this will be the main topic for my presentation today. So in order to provide drinking water quality, we have this kind of the process. We have the oxidation, we have disinfection, but we also have some kind of reaction that will also end up with the formation of disinfection byproduct. We have the desired effect using the technology or the process of oxidation and also disinfection. But then the desired effect, if in comparison with the undesired effect, also give the things that need to be considered carefully. The desired effect of using disinfection, we can successfully eliminate all the microorganisms, bacteria, viruses, protozoa. The other desired effect of using disinfectant or oxidant is the oxidation process, which can be remove all the micropollutants such as pesticide, cyanotoxin, and also the pharmaceuticals. But then on the other side, we also have the undesired effect, which is the formation of disinfection byproducts. So what is actually disinfection byproduct itself? As I mentioned before, the history or the proof that drinking water disinfection was a major public health triumph of the 20th century. So we have the water. We want to provide quality of drinking water to public, but then if in our water we have the precursor, we have natural organic matter, we also have the inorganic such as bromide or iodide, then we will end up with the disinfection byproducts or DBPs. So a little bit about the precursor, we have the organic compounds in water body. What is the organic compounds? All natural waters will contain what we call natural organic matter or NOM. And where's this kind of chemicals derived from? They can also, they will come from some material living like such as bacteria, some decaying process from the plants, for example, like from the leaf, from the bark, also from wood, and also from the human intervention. So there are wide range of molecular weight of the compounds or natural organic matters. We have low molecular weight NOM, what we call non-humic substances. We also have a high molecular weight natural organic matter or what we call humic substances. This is really the problematic in our water, especially if we're dealing with the using of disinfectant, because this kind of chemical, they are water soluble, and there are some polar functional groups, for example, like carboxylic acid and also the phenolic stuff. This is the structural feature of natural high molecular weight of natural organic matter. As we can see here, there are so many functional groups we can find in organic chemicals. So the sum up for the disinfection by products, we have the precursor, we have disinfectant, then we will end up with the formation of disinfection by products. As I mentioned before, the precursor of this material will be organic, natural organic matter, which is already naturally present in the water. And then if our water contain also very high concentration of inorganic, such as bromide or iodide, then when we make a contact with kind of disinfectant, then we will end up with the DBB's formation. This is the green part here. They mentioned about the information about the type of oxidant used in any countries. Chlorine is very worldwide used as a disinfectant because it's very cheap and also very stable, very reactive, can eliminate any microorganism in less than 5 minutes, very short. And then we have also ozone. Ozone is preferred use in France and also in Swiss. Chloramine, widely used in US. And also chlorine dioxide used in a European country. And then we also have the newcomer, the UV. So about the disinfectant byproducts, a little bit detail. So this is kind of the disinfectant byproducts in both parameters. So we have chlorinated disinfectant byproducts. We have iodinated disinfectant byproducts. We also have the brominated disinfectant byproducts. This guy, the brominated disinfectant byproduct is really problematic in our water. So that's why in Australia, this is a little bit case because in some part of the Australia, especially in Western Australia, they have a very high bromide concentration in their water. So if we have a bromide in our natural water, we use the disinfectant, especially the chlorine one, then we will end up with the formation of brominated disinfectant byproducts. And also, sometimes we also produce bromate, BrO3-, which is also very toxic. The last graph here showing the level of toxicity. So again, iodinated disinfectant byproducts is more toxic compared to brominated and chlorinated analogs. This is one of my research that I did when I did my PhD. So study the effect of bromide during the chlorination, and we end up with the conclusion that if we have a bromide and then we use bromine and also the chlorine, we will end up with the formation of brominated disinfectant byproducts and also the combination with being chlorinated and also brominated disinfectant byproducts. So I try to make the illustration here. So if we have organic precursor dissolved organic matter in our water, we disinfected with chlorine, then we will end up with the formation of brominated disinfectant byproduct through the electrophilic reaction. At the same time, the bromine will be oxidized to bromide through the electron transfer. And because we have a chlorine, for example, we have a chlorine in excess, the bromide will be recycled to form bromine, and then the bromine will react further with the reactive site of dissolved organic matter to form more AOBR formation. We also find the interesting part here that if we pre-chlorinated this dissolved organic matter consists in our water, then we will end up with the formation of chlorinated disinfectant byproducts. But then when we have the bromide in our system, the bromide will react with the chlorine to produce bromine, and then the bromine will also react with this dissolved organic matter to the organic reactive site. And then some part of the bromine will also substitute the chlorine side to form more brominated disinfectant byproducts. So this is the current research conducted in the US. This is already accepted in Water Research Journal. The volume is 289. This will be published next year. And this guy, this lady, Susan de Richardson, she's a big person in water research area. So one of his students just published this work. They try to measure the concentration of the waters, and then they find out that in their drinking water distribution system, from the raw water, finished water, and then through the distribution system, in 2 hours, 12 hours, 24 hours, they find the disinfectant byproducts. So in total, they found that 66 disinfectant byproducts in their distribution system. What I want to show you here, this is the result in the chloramine and also in the chlorine system. The formation of the disinfectant byproducts through the chloramine system, they can find or they can detect the concentration of the DPPs in about 40 microgram per liter or around 40 ppb. In the chlorine system, they receive almost the same concentration. And then in terms of, okay, we have a very US a very good advanced system in the water treatment process. They also have a very good drinking water distribution system. But why they can still end up with the formation of disinfectant byproduct? Is it hazard for the consumer? So the question is that in every country, they have what they call maximum contaminant level. So for example, for THM is a one small group of the disinfectant byproducts, trichloromethane. This is the combination between chloroform, bromoform, also iodoform. And according to the US EPA, the maximum contaminant level for this kind of chemical is 80 microgram per liter. So as we can see from the graph here, in their drinking water distribution system, they can detect the concentration of the DPPs around 40. This is for the yellow line, the row 2. When I check the supporting information, the raw data for this kind of the water in the row number 2 is very high in natural organic matter, and also they have some bromide as well. So even they can detect the DPPs in their drinking water distribution system, but again, the concentration is still below the maximum contaminant level regulated by US EPA. I want to talk about the public perception about water reuse, but I will just quickly show you the graph here. What I want to show you that this is the case of the Perth, Western Australia. According to this prediction, the water demand in 2060, according to the population, is about this much. So they need 255 gigaliter by 2060. So right now, their surface water and then groundwater and also from desalination, they cannot fulfill the water demand by 2030 and 2060. That's why they come to the very extreme idea. How can they use the water use? The water use in Western Australia concept is like this. They use the advanced treatment to treat their wastewater treatment plant. So instead of discharge their wastewater into the ocean, they treat it very well, and then they end up with very high quality of water from water use. And after that, they injected their treated water into the injection bore, into the groundwater, and mix with the groundwater naturally present in the groundwater. And then after that, they will leave it for, let's say, 20, 50 years. And after that, they will pump it again, do the process again, do the treatment again. After that, they will provide very high quality of water into the customer. This is very extreme, but this is the strategy that they need to do because in Australia, especially in Western Australia, water is very scarcity. So in terms of the treatment trends, especially when we dealing with the chlorine, before 1910, we use disinfection press and then followed by filtration. But after 1960, the filtration press, then followed by disinfection. But for today, they do the combination. We have the raw waters. We make sure that we did the pre-chlorination, and then we do the flocculation and also the sedimentation, followed by filtration. And after that, we do the final step, final chlorination. So I just want to conclude here in terms of our situation in Indonesia, particularly in Papua. We don't have any problem with drinking water resources. We have plenty of surface water, and in some case, we have surface water already contaminated or polluted by wastewater. We still have other option. We still have a groundwater, and then if we have a groundwater already polluted, then we still have rainwater. So there are plenty of water resources. But then we need to, in terms of providing very good quality of water, drinking water for the public, maybe we need to thinking about the use of disinfectant. Okay, because in terms of the health risk of disinfection by products, they are really small compared to the health risk caused by the waterborne disease. And according to the research, the acute health risk of pathogenic microorganism in drinking water is much higher, about 100,000 to 1 million times higher compared to the risk of long-term exposure to this disinfection by product. Okay, I think that's for my presentation. I
Thank
don't know
you
if I
so
already
much.
spent more than 10 minutes.
It's very, very good presentation. Thank you so much, Dr. Langsa. It's very fascinating presentation. So I think because you can wrap up your presentation is very effective time. We still have like 2 or 3 minutes for Q&A time. But before I open questions for the participants, I have one questions first. So.
Yeah.
As you know, in many cities across Papua, Manokwari and Jayapura also, most people rely on refillable drinking water, or maybe we call galon air isi ulang, provided by local small-scale enterprises, small business, home business. So from your perspective as an environmental chemistry scientist, how do you view the quality and safety of this refillable drinking water in our regions? And what practical advice can you give to us consumers, also me, so we can easily identify and choose safe, high quality drinking water for daily use?
Okay, thank you so much, Bu Octolia. I think this is the question that always asking or also deliver for everyone every
Yes,
time
I believe so.
every time I deliver my topic about water quality. Actually, we have no other option, to be honest. because because of our habit, we found that refill water is very practice, very efficient. We just bring our gallon or container, go to the refill shop, and then immediately, maybe 5 or 10 minutes, we receive our water. And then in terms of the quality, to be honest, sometimes I found that the shop, they're very proud if they found that their TDS, total dissolved solid parameters for the water quality is less than, for example, like 10 or 20 ppm. Actually, we still need some minerals, like some ions in our waters. So let's say that if the TDS, total dissolved solids from the produced water, less than 20 or let's say 10 milligrams per liter, we don't have we don't receive any minerals left in the waters. But in terms of the microbiology, microorganism, uh, our public seems like they're okay. They accept the quality because we can get the water from the shop and then we can consume directly. No complaint about the sickness, the disease regarding with the waterborne disease. So again, it's up to us. I also use refill water, but think about, okay, maybe I need to organize the water quality. Maybe I can use my own groundwater resource. I can control the mineral or the ion content, but at the same time, I also can provide the safe drinking water for me and also for my family. I hope this answered your question.
Yes, thank you so much. Yeah, like you said, we have no other options, but I believe we still can choose the best water for us. Okay, we have 1 more minute. Maybe any other questions? Maybe from Manokwari? Oh, there's one more question from the chat box. I will read for you. Thank you for your. It's from Mrs. Eva Simaremare, my colleague from Universitas Cendrawasih, Dr. Langsa. So I will read it, the questions for you. Thank you for your new insight from your presentation. What do you think about how can water purification technology be used by water companies or water refill business in Papua to reduce the very high level of minerals, lime, and other metals in our society?
This is very interesting questions. Thank you, Bu Eva. Okay, again, depends on the water company itself. If they claim that the technology that they use, for example, like reverse osmosis, then we will have free minerals, free ions left in our water. Because reverse osmosis is like it can filter any species, any chemicals, any materials, microbiology, things like this in one Armstrong. So this is like a 10 times minus 10. So it's very, 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 very small. Any ions, any species, any minerals, any microbiology will be filtered. So there's nothing left. So definitely this will be okay for our health. But then again, considering some minerals that we need in our body for the metabolism things, then definitely we need some minerals, right? Like calcium, magnesium, and also iron in our body. So again, it's depends to us.
Okay. So thank you so much. I believe there's still some questions, but the breaking rooms already open. So I am very sorry. I have to close these sessions. Once again, a big applause for Dr. Marcus Herianto Langsa. Thank you for the presentations. A certificate of application and signed by you also. Thank you so much, Dr. Langsa, and
Thank you. Yeah.
everybody, and also for the committee of the first Papua International Conference on Biodiversity, Natural Science, and Technology 2025 UNIPA. Thank you also for the opportunity for me to moderate these two sessions. So I would like to close these sessions. Once again, I wish you a fruitful continuation of the conference. Have a wonderful day and see you in the next sessions. And I will give the time for the AMC in Manokwari. Thank you so much.
biodiversity, technology, and environmental conservation. Each room will host a different thematic discussion or presentation stream to accommodate the diverse topics and interests of the participants. Participants will be able to join their preferred session by selecting the appropriate Zoom meeting link provided in the event program or platform. Each room will have a dedicated moderator to facilitate the session, manage Q&A, and ensure smooth communication. Please make sure to check the schedule carefully to join the correct room at the design time. Technical support will be available throughout the sessions to assist with any connectivity or platform-related issue. So please join to all participants to the correct room. Thank you.